Hi there. In this video, we're going to talk about the powers of matrices and diagonalization. So we very often need to take powers of matrices, and what we mean by that is that we have some matrix, for example, A, and we're raising it to the power 2 or to the power 3, and so on. And when we're raising it by a certain power, it means that we're taking the matrix and we're multiplying it by itself that many times. So we can see that this can be quite a difficult and tedious thing to do for large matrices that have, a huge number of rows and columns and so on. So this is where diagonalization comes in. So diagonalization allows us to convert the matrix into a different kind of form, and then using that form in that certain way allows us to use it as a kind of shortcut to compute powers of matrices in a more efficient manner and requiring less computing effort. So before we show that, we're just going to look at why we actually take the powers of matrices. What does it even mean to multiply a matrix by itself? So we're going to do that by considering a scenario, and that scenario is the population movement between different regions. So we can have two regions. We can have region A and we can have region B. So people are moving between these two regions, and this happens every year. So maybe by the end of a certain year, we would have found that 20% of the people in region A have moved to region B, and maybe 50% of the people in region B have moved to region A. So what that means is that 80% of the people have remained in region A, and 50% of the people have remained in region B. Or rather, 50% of the people in region B have remained in region B. So this is happening right throughout the year. And at the end of the year, we can try and determine how many people are in region A and how many people are in region B, given these different proportions of people staying and moving between the different regions. So we can create a matrix that actually captures this kind of movement. And that matrix would actually be a 2 by 2 matrix, and in the first column we will have 0.8, which corresponds to the number, or rather the percentage of people remaining in region A, and 0.2 representing people, proportion of people who are moving to region B. And in the second column we'll do the same with B, so it'll be 0.5 and 0.5. What we're now going to do is to consider what it actually means to calculate the proportion of people that are left in the different regions. So let's just say in year 1. So year 1. And let's just say as a starting point, everyone is in region A and there is no one in region B. So we're going to say that corresponds to the vector 1, 0. So if we multiply this 2 out, what we're saying is that we have, at the end of year 1, 80% of the proportion of people in region A plus the proportion of people moving to region A from region B. So we can see that it's going to be 0.8 times 1 plus 0.5 times 0. So I'll just say that again. This 1, 0 is representing the proportion of people that are currently in region A and currently in region B. And our starting point we're saying is that everyone is in region A and no one is in region B. So when we multiply this out, we are saying that 80% of the people in region A, which started off as being 100%, are going to remain in A, and then plus 50% of the people in B moving to A. And then we do the same thing for region B. So 20% of A have moved to region B, and 50% of region B have actually remained in region B. And of course, we said our starting point is 0. So what that means is that at the end of year 1, it's equal to 0.8 and 0.2. And what this means is that at the end of year 1, 80% of the people are in A, and 20% of the people are in B. So we started off in year 1 with everyone in A and no one in B. And at the end of year 1, we have 80% of the people in A and 20% of the people in B. So what we're going to do is just repeat this for year 2. So we have this same matrix. That's 0.8, 0.5, 0.2, and 0.5. And now, at the start of year 2, we have 80% of people in region A and 20% of people in region B. So we're going to bring that down. So we have 0.8 and 0.2. And then performing this same calculation, it's going to be 0.8 times 0.8 plus 0.5 times 0.2 and 0.2 times 0.8 plus 0.5 times 0.2. So what this is going to give us is 0.74 and 0.26. So we're just going to repeat this calculation 2 more times for year 3 and year 4. So in year 3, we have the same thing, 0.8, 0.2, same matrix, 0.5 and 0.5. And now at the start of year 3, we have 74% in A and 26% in B. And if we perform this multiplication as we have done previously, we'll get the result 0.722 and 0.278. 0.278. And then one more time, we do it for year 4. We have the same matrix, 0.8, 0.2, 0.5, 0.5. And now again at the start of year 2, we have 0.722 and 0.278. And that gives us 0.717 and 0.283. So what does this mean? What this means is that if we keep carrying on doing this multiplication, we can see that there is not a significant difference in the results that we are getting. If you compare this for year 3 and year 4, 0.722 and 0.717, and also 0.278 and 0.283, you can see that it seems like as if they are approaching a constant value, and that is the case. So if we just were to try and plot that quickly, so on the x-axis we have years, so that's year 1, year 2, year 3, and year 4. And at year 0, we said that it's 100% the proportion of people that are in region A, everyone is in region A, so we started off here. And then we kept doing this calculation to calculate the proportion of people in region A, so this is region A. And at the year 3, we had 7.22, 0.722, and 0.717. And let's just say this is 0.717. 717. So we started off perhaps here. And we can see that it kind of starts approaching a constant value at a certain point. So beyond, if we go year 5, year 6, year 7, year 8, and so on, it would just approach that constant value. So that means that what is happening is that that constant value, we say, is approaching some kind of steady state. So physically, what that means is that if we have this kind of system, this population change happening like this, where we have a certain proportion of people moving between these two regions and staying in this certain region, if everyone starts out in region A and, after a certain period of time, after a certain number of years, the amount of people in A and the amount of people in B are not going to change. They're going to reach that steady state. They're going to reach that constant value, even though throughout the year there is that movement of people. So multiplying matrices actually captures this effect. So when we are multiplying matrices, we are actually moving towards trying to determine the steady state of some kind of system. So let's just write that out in terms of our matrix. So we said that our matrix was 0.8, 0.2, and then we have 0.5 and 0.5. And we multiplied it by 1 and 0. That's at the start of year 1. So this is year 1. Call it year 1. And then we took the result that we got and then we multiplied it by the matrix again. So 0.8, 0.2, 0.5, and 0.5. And that corresponded to year 2. So I think you can see where this is going. We then took this and multiplied it again. 0.8, 0.2, 0.5, and 0.5. And this now became year 3. And we did it all the way up until year 4. So in other words, what we've done is that we have taken this matrix A and we multiplied it by itself 4 times. And then we multiplied it by this vector, which we can designate by x. So that means that what we are doing now is that we need a way in which we can compute this a to the power 4. And the shortcut that I explained now in how this can be done is by the procedure of diagonalization. We're just going to now explain the procedure and the formula for diagonalization. We're going to derive it, and thereafter that we're going to illustrate how to perform this calculation using this same example. So in a previous video, we had spoken about eigenvalues and eigenvectors. We had shown the formula where we have a matrix A, we multiply it by its eigenvector, and this is equal to its eigenvalue multiplied by the eigenvector. So this is our starting point when we speak about diagonalization. So what we're going to do is we're going to create a matrix, call it M. And what this matrix has is that it consists of eigenvectors of A. So this matrix is the eigenvectors of A. So that would be x1, x2, x3, all the way up until xn. So the columns of this matrix are the eigenvectors. And these columns would correspond to the eigenvalues of each of these eigenvectors. So that's 2, that's 3, and the nth eigenvalue. So now what we do is we take this matrix A and we multiply it by this new matrix that we have created, which consists of each of the different eigenvectors as the columns. So this is going to equal to, we have our new matrix M, so that's x1, x2, x3, all the way up until xn. And if we are multiplying this by A, then we're multiplying the columns by A. And now if we compare this to our equation that we had just written, we can see that it's equal to lambda I xi, so we just replace that. So this becomes lambda 1 x1. So we have taken this and substituted it in here. And we do the same with the other terms. So we have lambda 2 x2, lambda 3 x3, and lambda n xn. So the next step that we're going to do is that we're going to pull out all of these eigenvalues. So we have x1, x2, x3, xn. And when we take out all of these eigenvalues, it becomes a matrix. So in the first row, we would have lambda 1, and then we would have zeros all the way till the last column, which would have the 0. And then the eigenvalues essentially form the diagonal of this matrix. So the second row, second column will have lambda 2, and then the rest of the row would have zeros. And it carries on like that, with the third row and third column being the third eigenvalue. And in the last row and last column, we would have lambda n. We can see that if we multiply this matrix by this matrix, then essentially we'll be multiplying each term of this column by the various eigenvalues in this matrix that we have just created. We can just recall now that this is this matrix A times M. So we have A times M, and this is equal to this matrix M, so that hasn't changed. Now multiplied by this new matrix, which consists of the diagonals, which consists as the diagonals being the eigenvalues. We'll call that D. I'll just repeat that. This D is a matrix which contains in the diagonals the eigenvalues. So we want to isolate matrix A. And in order to do that, what we have to do is multiply both sides by the inverse of matrix M. So if we do that to the left-hand side, we get that A is equal to this matrix M times this D. So matrix M is a matrix which has the columns consisting of the eigenvectors. Matrix D has the diagonals of eigenvalues, and then we multiply it by this matrix M, the inverse of it, the inverse of matrix M. That gives us A. So now what we want to do is think of this in the context of raising a matrix to a certain power. So let's just say we want to raise matrix A to the power n. We want to raise matrix A to the power n. So let's do that. We then raise this right-hand side to the power n, so it will be m d m to the minus 1, all raised to the power n. So what that would look like is we have m times d times m to the minus 1, rather the inverse of m. And then now raising it to the power n means that we're multiplying it n times. So we're going to multiply it now by the same thing. We have m dm to inverse of m. And this matrix is going to be multiplying itself many times, all the way up until we have n times. So the last one would be m d and the inverse of m. So we see something happening here. We see that this m inverse and this m, well, that's just going to cancel out, so to speak. And that's going to happen the number of times that we've multiplied this matrix out. So what we're left with is this first term, so that's m. Then we have this diagonal matrix, so that's multiplied itself out n times. And remember, the diagonal is just a whole bunch of zeros with the diagonals consisting of the eigenvalues. So if we are raising this matrix to a certain power, all we're doing is just raising the eigenvalues to that power. So we have this diagonal matrix, eigenvalues raised to the power n. And then the last term that we have is this inverse of m. So this is how we would actually compute a matrix raised to the power n. All we just do is we compute this eigenvalues and eigenvectors. Then this matrix M, we just put the eigenvectors inside there. then we take this eigenvalues, we just raise the eigenvalues to a certain power and then put them in this matrix. Then we compute this inverse of m, and then that's it. That's this a raised to a certain power of n. So we can now apply this to this example that we had earlier. We had this matrix A which was equal to 0.8, 0.2, 0.5, and 0.5. And what we had done was that we had raised A to the power 4. And this, using this formula, is just equal to this matrix M, this diagonal matrix to the power 4, and the inverse of this matrix M, just multiplied together. So we can now use this formula for this matrix. So the first thing we need to do is determine the eigenvalues and the eigenvectors. And to do that, we use the characteristic equation, which we had derived in a previous video. We had seen that the characteristic equation was A minus lambda I is equal to 0. So this would be essentially 0.8 minus lambda, and then 0.2, then 0.5, and 0.5 minus lambda. And we set this equal to 0. So we solve this determinant. So that would be 0.8 minus lambda times 0.5 minus lambda, and then minus 0.5 times 0.2, which is 0.1. Set this equal to 0. So this is quite an elementary quadratic equation to solve. It's a fairly simple matter to solve this. And when we solve this, we find two values of lambdas. We have lambda 1, which is equal to 1. And then we have lambda 2, which is equal to 0.3. So in order to find the eigenvectors, what we have to do is we take this equation, which is A minus lambda I multiplied by this eigenvector, and we set this equal to 0, and then we solve for the eigenvector. So A minus lambda I, okay, so we have to do it for two values of lambda. We have to do it firstly for lambda equal to 1, and then lambda equal to 0.3. So let's do it now for lambda equal to 1. So we'll have this, our matrix. Our matrix was 0.8, so we're going to have 0.8 minus 1 and 0.5 minus 1. So 0.8 minus 1 is just minus 0.2, then we have 0.5, then we have 0.2, and then 0.5 minus 1 is minus 0.5. And this eigenvector, we can call it x1, x2. This is equal to 0. So we can see that row 1 and row 2 are virtually the same thing. So we have minus 0.2 x1 plus 0.5 x2, which is equal to 0. So what that means is that 0.2 x1 is equal to 0.5 x2, or we can say that, x2 is just 2/5 of x1. So x1 is arbitrary. We can choose essentially any value of x1. So now we do the same, but with lambda equal to 0.3. So if we do that, we're going to have 0.8 minus 0.3, so that's 0.5, and then 0.5 here remains the same, and we have 0.2, and then we have 0.5 minus 0.3, which is 0.2. And this is multiplied by the eigenvector x1, x2, and this is equal to 0. So again, we can see that x1 and x2, row 1 and row 2 are virtually the same. So what that means is that x2 is equal to minus x1. So again, we can choose any value of x1, and we can substitute and do the same for x2. So we can now create this matrix M that we spoke about earlier. And we had said matrix M basically consisted of the eigenvectors. And the first eigenvector, where lambda is equal to 1, we can choose any value of x1 and x2. So we can choose basically, so the same proportion. So we can choose x1 equal to 5. x1 is equal to 5, and then we can choose x2 to equal to 2. And with x1 and x2, we could choose, x1 to be minus 1, and since x2 is just minus x1, so it means that x2 is just 1. So we have formed this matrix M. So the next thing that we have to do is we've got to find the inverse of matrix M. So that's the minus 1. And this is equal to 1 over the determinant of matrix M multiplied by the adjoint of matrix M. So 1 over the determinant, so that would be 5 times 1, which is 5, and then minus 1 times 2, which gives us plus 2, and then the adjoint of matrix M, so we swap 5 and 1, so this becomes 1, and that's 5, and then we don't swap minus 1 and 2, but we do change the sign, so that becomes 1, and that becomes minus 2. So this is now equal to, if we multiply out, we have 1 over 7 and we have 1 over 7, and we have basically minus 2 over 7 and 5 over 7. So this was this matrix M. Then now we have this diagonal matrix D, and this consisted of the eigenvalues in the diagonal, so that's 1 and 0.3. However, we are raising this diagonal to the power 4. So 1 to the power 4 is just 1, and 0.3 raised to the power 4 is 0.081. So the next step is to just compute this M times this diagonal to the power 4, and that's going to equal to 5, 2, minus 1, and 1. And then we have 1, 0, 0, and then 0.0081. We can just multiply these two matrices. We're going to multiply row 1 and column 1 to get position 1 of this new matrix, and then we take row 1 times column 2 to get position 2 of the first row. Then for the next row, we're going to take row 2 times column 1, and then row 2 times column 2 for the second row, second column element. So if we do that, we're going to have 5 times 1, which is 5, then plus minus 1 times 0, which is just going to be 5. So that is 5. And then we're going to take row 1 times column 2, so minus 1 times 0 gives us 0, and then we have minus 1 times 0.081, which is going to give us minus 0.081, so minus 0.081. Okay, there's an extra 0 here, so we have minus 0.0081, and then we're going to take row 2 multiplied by column 1. 2 times 1 is 2, and then 1 times 0, so that just gives us 2. And then we have row 2 times column 2, 2 times 0, then 1 times 0.081 is just 0.081, 0.0081. And then the last and final step is we got to apply that formula. So a to the power 4 is equal to m d to the power 4 times the inverse of m. So we have computed this md to the power 4, that's that, and then we just multiplied by the inverse as the final step. So this would be 5, 2, minus 0.0081, and then 0.0081, and then this inverse of m, and that was equal to that. We just bring that down. So that was 1 over 7, 1 over 7, and then we had minus 2 over 7, and 5 over 7. So if we just multiply out this matrix as we had done previously, so it's going to be 5 times 1 over 7, then plus minus 0.0081 times 2 over 7. So the minus and the minus will give us a plus there. So if we do that, we then get 0.717. And then we do the same here for column 1 and row 2, 5 times 1 over 7 minus 0.081 times 5 over 7. That will give us 0.7085. And then lastly, we have row 2 times column 1, so 2 times 1 over 7 minus 0.0081 times 2 over 7. And then that gives us 0.283. So that's 283. And lastly, row 2, column 2, 2 times 1 over 7 plus 0.0081 times 5 over 7. So that will give us 0.2915. So if we just compare this, 0.717, 0.283. So remember, if we go all the way back up to where we were talking about steady state and population growth and all of these things, we can see that when we computed this year 4, we had 0.717 and 0.283. So this was the same as taking this fourth power of this matrix and multiplying it by x. So this x here we said was 1, 0. So we just bring that 1, 0 down. So we have this, we multiplied by 1, 0. We said everyone was in region A. Then when we do that, we get 0.717 and 0.283, which is what we had actually seen when we had multiplied this matrix and raised it to the fourth power and taken it in year 4. So this may have been maybe not that simple for just 2 by 2, because we could easily multiply out the matrices for 2 by 2 matrices. But we can see if we have large powers of matrices, for example, a 5 by 5, and we have to multiply a 5 by 5 matrix by itself 4 times, we essentially multiplying that, it's going to take a lot of time and effort and computing power to do that. So in that instance, it's easier to apply this diagonalization equation to actually determine the power of the matrix. So thank you very much for watching.